Okay, hello. Good morning, everyone. Let me say thank you first for the organizers, in particular Campi, for the invitation. It's really a pleasure to be here. I have prepared these talks mainly for the students. I don't see many of them here, which is a pity. They will come slowly. But I hope my lectures will be, at a level that everyone can understand. And yes, I should say sorry for the lecturers and the researchers. I don't really care much about you. I care about the students. And that's my aim here, to teach the students. So students, feel free to ask me questions. The only person who should be afraid of asking questions, of the questions here, should be me. You should not be afraid of asking questions. I should, because most probably I will not be able to answer your questions, and I will be very embarrassed, because I'm supposed to be a professor in cosmology with more than 20 years of experience in this, and you will realize if you ask me lots of questions that I don't know the answers to many of them. So don't be afraid of asking questions. I will be afraid of your questions, okay? I'll be the one being embarrassed, not you. And just to give an example, many of the students are afraid of asking questions because they think the questions are very stupid. And I learned one lesson when I was a PhD student in England, and I was in a seminar, and someone, a professor there was a seminar about the cosmic microwave background radiation, which hopefully all the students know what this is about. And someone in the audience asked a professor, what is the redshift of the last scattering surface? So when was the cosmic microwave background radiation released? Okay, what's the redshift? The students, do you know? Yeah? No, but you're not a student. Come on. No. I'm talking to the students. Students. You know the CMB, the cosmic microwave background radiation? You have heard about it, yes? The primordial photons which were created at the time of Big Bang inflation, yeah? When did the universe become transparent? Last scattering surface. That's what we call. Well, for those who do cosmology, maybe you... No students have an idea? At what redshift is the last scattering surface for the CMB? Maybe your cosmology is not as good. Anyway, the lecturers, do they know? The redshift? Yes, you're saying it's about 1,000. Yes, redshift around 1,000. Okay? So the person was this. So this is something. It's maybe the students, you didn't take a cosmology course properly on the CMB, but it's a very basic question. Let's say for someone who does cosmology and observations, and the person who asked this question in the audience was Stephen Hawking. Okay? So, like, I knew the answer for the questions. I think all the students in that audience, because we do cosmology and we work on the CMB, we knew the answer for the questions. So when Stephen Hawking is asking a question, he does not know the answer, and I know, that's the day I learned, you can't know everything. Even Stephen Hawking does not know everything. Okay? So what I'm trying to say, I don't know everything. You students, you don't know everything. Well, you don't know what's the redshift of the CMB. I just found that out. Okay? So feel free to ask me questions. I don't know if I'll be able to answer, but feel free to ask me questions. Okay? And I can assure you, hopefully, I'm not alone. There are other lecturers and researchers in the room. So even if you ask me a question I don't know, maybe one of your teachers here knows the answer for them. So it should be okay. The aim is that we learn something with here. And and in particular, I should also say this is, I think, very important because you are here, I'm here, thankfully to the taxpayers in Thailand. So there are people in Thailand who pay their taxes for me to be here. And I'm sure the topic that I'm talking about, gravity beyond Einstein's General Relativity, it's not maybe on their top priorities in their lives. Maybe there are other priorities they have about life. So let's make the most of it, okay? For the taxpayer money of these people, in Thailand. It's just a question of respect, I think. So I will do my best to teach you. please do your best to ask me questions. If you're afraid of asking questions in the audience, that's okay. Afterwards, at coffee break or lunchtime, come and sit with me, come and talk to me, okay? And we can ask these questions. Very good, so let me start now. So I will try to keep my time in about 1 hour per lecture, so because then you get very tired. And I will also try to speak a bit more slowly. I forgot, so English is not your first language, so I'll try to speak a bit more slowly. And sorry, sometimes I get very excited and I speak too fast, but I will try not to do it. Good. So my lecture is going to be in general about cosmology of gravity theories beyond general relativity. Basically my aim with these lectures is to tell you a little bit, it's a huge field of course, a little bit of what cosmology can tell us about gravity beyond general relativity. In particular, what are the cosmological probes, methods to test gravity theories. So I will give you just a very general introduction to the theory of gravity beyond general relativity. I will be very specific in some models, hopefully much simpler than the ones that you have heard up to now. So very, very simple ones. And then my lectures are going to be a lot about observational cosmology. So I know many of you are theoreticians, so I will make the lecture hopefully not as boring as that, because I know you like theory. But you should be theoreticians who try to live in the real world. When I was your age, I just wanted to do theory. And then you realize there are many theoreticians, there are many ideas in the universe, on planet Earth. Theoretical physicists, we have a huge imagination, sometimes more than artists, because we invent lots of things. But the universe only follows one set of laws, so we always have to check our theory against observations. And so I changed my career. I was a theoretician, and now I'm more on the observational side. Okay, so let me start. So let's see if I can get this right. So let's talk about gravity beyond general relativity. So in very simple terms, let's start with general relativity. So what is general relativity? So general relativity, in a very strict sense, is basically a theory where gravity is mediated by one field. And this is, in general relativity, this is a spin-2 field, okay, the tensor. So that's going to be maybe the quantum field view of an interaction is you have two particles, they interact gravitationally because they will exchange a spin-2 field. Of course, general relativity is a classical field theory, so it's not quantized, but that's one way of saying it, okay? Now, in general relativity, this spin-2 field is also the geometry of your space-time, as you know that. Okay? And you might say, okay, that's very trivial. We know that. Yeah, I'm quite sure you know that. Okay, so there's one field. That's the gauge boson between particles, and that spin-2 field is also the metric, the geometry of your space-time. Now, one way of very simply going beyond general relativity is basically to include more fields on the gravity interaction. So we have extra carriers of the gravity interaction. So the gravity interaction only has one carrier, is the spin-2. Like electromagnetism, we only have the photon. But the strong interaction has 8. The weak interaction has 3 gauge photons, gauge bosons. Yeah. So they have more extra carriers of the interaction. So one way of going beyond general relativity is to include extra degrees of freedom, extra carriers of the gravity interaction. And you can include, for instance, scalar fields that you have heard about a lot. You can include vector fields and even other spin-2 fields. Like yesterday on the lectures by Antonio De Felice, Diane was talking, he mentioned, for instance, biometric theories of gravity, where you have 2 spin-2 fields. Okay, so this is one way. So now we are going beyond general relativity. And now you ask the question, okay, but general relativity, gravity is comes from the geometry of space-time. Yes, so what is the metric of your space-time in these extended theories of gravity? Well, the geometry of the space-time can come not from the spin-2 tensor, but can come, for instance, from a combination of all these other fields. And this is for just an example of a combination of the scalar field and the vector field and the tensor field. Okay, it's just a simple combination, which is used in some theories of modified gravity, this one. Okay, so one way of going beyond general relativity is that you introduce extra fields, and then you ask the question, what is my geometry? And the geometry might be a combination of these fields. So the geometry of space-time is not just G mu nu. It's not just the spin-2 field. It's a combination of the other ones. Okay? Good. So, I can, sorry? This is a disformal transformation, yeah. Yeah, good. But I think, yeah, it's a disformal transformation. So it's a very well-constrained theory of modified gravity is this happen. But I'm not going to work on this one. It's just an example of possible theories of gravity. Yeah. So this is a disformal transformation. That's right. And this leads usually when you have these extra degrees of freedom, where you have the geometry of space-time is not just your spin-2 field. Usually this leads to equivalence principle violations. Okay? And I will tell you a little bit about the equivalence principle. Okay, so let me bring a bit of general relativity. So usually what you have Lagrangian, the action for your matter fields, psi. Yes, and these matter fields, since we are in the metric theory of gravity, so we see gravity as the geometry of your space-time, we'll feel what is called the physical metric, sometimes called also the Jordan metric. We call it physical. So particles in the universe, they feel this G mu nu. Okay, so they live in a space-time where there's G mu nu, that what give you the geometry of your space-time. So the metric of your manifold. Now, you also, since you have a gravity interaction, you should have also an action, or Lagrangian, for your gravitational field. And that does not represent the metric of your space-time, just the action for your gravitational field. And that's the usual Einstein-Hilbert action that you know, basically is the Ricci scalar, where you have here, for instance, the determinant of your gravitational metric, the G star there. Okay? So one thing is the geometry of your space-time, the other thing, and the action for the geometry of the space-time, for how your matter fields feel, what's the geometry your matter fields feel, and the other one, what's the Lagrangian for your field in itself. Okay? So I said in general relativity, G mu nu and G mu nu star, they are the same. Okay? They're the same. That's what I'm telling you again, what I told you just before. What is what? G star? Okay, I will show you some examples. But here G is just the determinant. You know this action? The Einstein-Hilbert action? Yes. So that's just the determinant for this G mu nu star. So it's going to be the spin-2 field associated to gravity. I will show you some very specific examples when I do. This is just a very general idea, okay? But what I want you to know is that one thing is the interaction between the fields, okay? And the other one is the Lagrangian for that spin-2 field. So you can think even electromagnetism, okay? So electrons, they're going to be spinors. They will be interacting with the photon. Okay, so instead of G mu nu, it's going to be A mu, the photon field. Yes, so we have the interaction between the electrons, the spinors, and the photon. Okay, that's an interaction term. And now you need also the Lagrangian for the photons themselves. And that's the equivalent to that. That will be the F mu nu term. that you get usually for the photons. Okay, so I'm trying to distinguish very explicitly. One thing is interaction with gravity, between matter fields and gravity, gravitational field, and the other one is the Lagrangian for the gravitational field. In general relativity, they are just the same, so you don't even think about that usually. Students, we don't even think about that. We just think, oh, it's the same. Okay, but it doesn't matter. It's not. Very good, so let me give you now the Newtonian limit of this equivalence principle with a little bit of GR. So let's consider a test particle. Okay, so this is the action basically for a test particle. So there's a given geometry, g mu nu. This is v is just dx dt. So the for velocity. Yeah, so that's usually the action. And if you want the equation of motion for this test particle, basically you just apply the variational principle. Okay, I think all the students know the variational principle, so you vary the action. And from that, what you get is basically the equation of motion for the test particle, which is also called the geodesic equation. And that's what it is. So basically, you have the for velocity now in a proper time, the covariant derivative, where it's basically the partial derivative plus the Christoffel symbols associated to g mu nu. I think you know that from GR. And that's equal to 0, so that's the geodesic equation, basically. And this gives you basically the for acceleration for the test particle. Okay? Very good. And if you assume the Newtonian limit, the weak field limit, you can expand the metric, your g mu nu, which will have g00 component and gii components, as -1 plus 2 phi c square. I think you've seen the weak field limit for the metric before. Okay, so when you plug the g00 into this covariant derivative, what you get is that the acceleration of the particle is going to be proportional to the gradient of this potential that we call the Newtonian potential. And you say, yes, we already know that. Probably, yeah? Yes, I will show that is the one of, yeah. Well, no, you just have the Minkowski metric that you assume, and you assume there's a perturbation to the Minkowski metric. The first order perturbation is going to be like a scalar perturbation, and that what gives you the Newtonian limit. If there is a fundamental, I'm not sure what you mean by a fundamental reason.
Didn't come from the equivalence principle. It's the extension of the Poisson equation to general relativity.
Yes, that's right. Which, yeah, I'm going the other way around. I'm starting on general relativity and I'm going down to the Poisson equation. Yes, yeah. Yes, I'm not sure. Yeah, we can talk at coffee time. Which direction we go? Yes, from the weak field, the Newtonian approximation to general relativity, or from general relativity to I think. I'm not sure what's the historical context, but I think the Newtonian gravity, since works so well on the low velocities, weak fields, I think Einstein made it so that it matches, I would guess somehow. I don't know. But I'm not an expert. This is the kind of questions that I don't know it for sure. Okay, let's discuss it coffee. Yeah. Okay, good. So what I'm saying is that a particle, a test particle living in a geometry will basically have an acceleration which is the gradient of the g00 component of the metric. Okay? That's the acceleration there. But this is here, it's pure geometry, as you can see. Okay, I didn't tell you, for instance, how matter is distributed in this in this space-time. So the way I need to know, if I have, for instance, so this is what I told you. So from there, you can define what is called the Newtonian potential. So the Newtonian potential basically comes from Newton's second law, where the acceleration is proportional to the gradient of this Newtonian field. Okay, that's the way we define the Newtonian potential. And in your head, you already associate, oh, but the Newtonian field is the gravitational field. No, not yet. Okay, stop it in there. The acceleration of the test particle is proportional to the gradient of a field. And that's in general classical physics, you know. If I have an electric field, the acceleration of a charged particle in an electrical field is proportional to the gradient of the electrical field. In the magnetic field, is proportional to the gradient of the magnetic field. Okay, so the acceleration of the particle is just proportional to the gradient of a field. And we call the Newtonian field because people related this to gravity. Okay? But I haven't talked about gravity. I will talk now. So what about gravity from a matter distribution in a given regional space-time? For that, we define the Poisson potential. Okay? So if I include some matter in the regional space-time with a given energy density, this matter will source a potential that we call the Poisson potential. Okay? So we have the Poisson potential and we have the definition of the Newtonian potential. So again, in this Newtonian limit, in the simplest theory of gravity, we have Newtonian gravity, and we just say that the Poisson potential is just the Newtonian potential. And you are taught in your courses very well, because this series works very well. This assumption is fantastic. Yes, because it works on our daily lives extremely well and is well tested, as you will see. You just make it in your brain the connection that these two guys, the Poisson potential and Newtonian potential, are the same. And this is crucial for all my talk and all these my 5 lectures that I'm going to give it to you, is that usually in theories beyond general relativity, this is not true. So the Poisson potential is not going to be equal to the Newtonian potential. Okay? Yes, precisely. Yeah. Very good. Okay? So these kind of things is applicable for theories which go beyond general relativity, both as an alternative, for instance, for the dark matter component. So people work with MOND, modified Newtonian dynamics. Usually that's the way they do. They change in fact, the equation of motion of the particles. They keep the Poisson equation, but they change this one. And people work, for instance, in modified gravity as alternatives to dark energy. That's the ones I'll be talking about here. Usually, we also do something similar. Okay? Good. Okay, so another summary. So usually you can think of gravity theories in a relativistic regime. So we always work with spin-2 fields, so with metrics or with tensors, that we have a physical metric, also the Jordan frame metric, that's sometimes called, okay? And basically matter, or standard model particles, they follow the geodesics of this G mu, the physical metric, okay? And that's the analog to the basically Newton's second law. But then you can also have an Einstein type of metric, and that basically gives you, it's a spin-2 field, that's the carrier of the gravity interaction, and that's going to be the analog to the Poisson potential. Yeah? Again, they are the same for general relativity, for Newtonian gravity, but in our theories of gravity, they can be different. So now I'm telling you some specific examples. One of the examples, for instance, is that I introduce a scalar field on my gravity sector as a carrier also of the gravity interaction, and I have what is called a conformal relation between the metrics. So my physical metric, my Jordan frame metric, is proportional to the Einstein one times the conformal factor. It's conformal because it basically depends only on the values of the scalar field, of the scalar degree of freedom in there. So that's going to be a conformal relation. And the theories of gravity that I'm going to show you, concrete examples today, they all fall more or less in this kind of relation. They're going to be conformal theories of gravity. And they are the easiest to study. They're not the most general one. The most general one are theories of gravity, which in fact have these formal relations. For instance, like this one, where the physical metric is basically a combination of, you have scalar fields, you have vector fields, you can have derivatives of your scalar field. So the relation between the two metrics, the Einstein and the Jordan one, does not depend only on the value of the field, but might also depend on derivatives of that. So these formal theories of gravity, they are very tightly constrained from gravitational wave measurements. For instance, of the speed of the gravitational waves and the mass of the graviton, for instance. So they are tightly constrained. It's not they are completely ruled out, but a big part of the parameter space is strongly constrained. But there's some loops in there. So I think that's still worth working. But for instance, if you do not believe in dark matter particle, if you think that dark matter is just an effect of a modified gravity, then usually conformal theories of gravity, they cannot be an alternative to dark matter. If you want to explain the dark matter phenomena, so galaxy rotation curves, for instance, without a dark matter particle, if you want to have a modified theory of gravity, then you need a this formal relation, because you need to change the photon geodesics, the null geodesics. Okay? And that you needed a this formal relation, because conformal relations, they preserve angles, so they won't change the null geodesics, as you will see later in this lecture. So this is just to give an example of different relations between the physical metric and the Einstein metric, and these different relations have different consequences for cosmology and for the universe and the observations. Very good. So the bottom line here is that particles will not follow your Newtonian potential. Okay? They will fill the acceleration, but the geometry is given by the combination of these things. Okay, so let's now be a little bit more formal, not a lot, but just to be clear, since this is a lecture, you should know that when we go beyond general relativity, including extra degree of freedoms is not the only way. There are several ways of going beyond general relativity. So the first thing that we should know is what is then general relativity? Well, what are the Einstein equations, or the Einstein field equations? So there's a theorem by Lovelock. I don't know if you heard about it in the lectures before, because usually people who talk about modified gravity give lectures, they usually talk about the Lovelock theorem. But basically, this theorem says that the only second order equations, which are local, that represent a four-dimensional space-time, and the carrier of the gravity interaction is a spin-2 field, is a tensor, then those are the Einstein equations with a cosmological constant. So that's the Lovelock theorem. So we have these four conditions. So the equations are second order, they are local, we live in a four-dimensional space-time, and there is only one carrier of the gravity interaction, which is this spin-2. When you do that, basically you are defining also general relativity. Okay, so we have this theorem. So if I want to go beyond general relativity, I have basically to violate one of these conditions of my theorem. Okay? And one example then, so if you have the Einstein-Hilbert action where R is the Ricci scalar, yes, you know that's the Einstein-Hilbert action for general relativity, where R Ricci scalar. So we have basically, in fact, 5 options. The 4 first ones, they violate Lovelock theorem. So one, you can add a new field. So here I've added a scalar field. It's a Brandis-Dickey type of theory with a given potential. So I just add an extra degree of freedom, so I'm adding a new field. So this is related to what I've just told you before. But you can keep, you may just have the option of not adding no other field, but just increase your space-time dimension. So if you're going to live in a 5-dimensional brain world, or in a 6-dimensional brains, or if you are in string theory where you live in 11 dimensions, then you just change the number of dimensions, and your geometry now is more than 4 dimensions. So now you're also violating the Lovelock theorem, so you are doing beyond GR physics as well. The other possibility is to have higher order derivatives in your equations of motion, which you have heard yesterday from Antonio, that when you do that, usually you are violating the Ostrogorsky theorem, so lots of instabilities and problems usually come from that. There is an exception to this, which is the f of r gravity theories, which I will tell you about in these lectures. But usually, if you want to have higher order derivatives, so terms where you have double derivatives of the Ricci scalar, etc., so your metric field, you'll have like second, third, fourth derivatives of your metric field, then usually you have these instabilities. But that's also a possibility that you can have, that you violate Lovelock theorem condition and you are beyond general relativity. And the fourth one is not including violating locality, so usually you have this box operator, inverse box operator in your Lagrangian, and usually you violate locality. And of course, the fifth one, which it's especially, I think, especially very important for the students, in fact, to know, is that maybe we are always assuming this action principle and variation principle to describe the physics in our universe. But maybe there's no such a thing. Maybe the universe does not follow an action or Lagrangian. We don't know. So as a student, sometimes I think we need revolutions in physics, and you should try to go beyond what old people like me and other people think about that, what are the laws of the universe. And you are young, so you have to go beyond what we think. Because the problem of dark energy is such a big problem that we cannot just add a new term on our Lagrangians and actions and think that the problem is going to go away. I think we really, in my opinion, we really need a revolution. And for the young people, that's what you have. So, in fact, I should have said also at this sentence here. Everything that I'm telling you now in my 5 lectures today, I am 99.99999% sure that in 500s from here, a physics professor will give a lecture and is not going to be talking about this. Hopefully, yes? Hopefully in 500s from here or 1,000 years from now, you know, physics has changed, you know, we have evolved, that we'll see the universe in a different way. Okay, so of course this series might reduce to this kind of equations, but hopefully we're going to be talking about a completely different physics. Okay, so I'm just telling what we know up to now, but you as young researchers, you have to think beyond. Okay, so you have to doubt everything I'm telling you here. Okay, always be aware. Yeah.
When you say that you add a scalar field, is that the same thing as to say that you add a new kind of particles, like the bosonic particles to like couple with gravity?
Yes, that's correct. But of course, when you add a particle, usually you think about quantum field theory, so you quantize the scalar field and it becomes a particle. I'm going to be only talking about classical physics, so in gravity. So these are just fields, and I keep calling them fields. Because usually when you talk about, oh, this is a particle, it means you have quantized your scalar field or your vector field, and you got the photon, you know? So you have to quantize the scalar field to get the Higgs. Then it's a particle. So before the quantization, well, I'm not an expert, but for me, before quantizing, you don't call things particles, you just call them fields. Yes, but it's similar. It's like having an extra boson for the gravity interaction. But I'm talking about classical physics, so we don't have bosons or fermions here, because, yeah.
Yeah, but
Yeah.
do we like expect to see new kind of particles here, like over the standard model, something like that? Like some new scalar particles that can interact with the gravity.
Yes, that's right. So we expect to see a new field or new particle here. And in fact, I won't have time to talk about that in my classes, but this field can even be observed in laboratory experiments. So for instance, if this scalar field, I told it couples to matter. So it will couple, for instance, with electrons. Yeah, so electrons will feel this extra scalar field interaction. So there are experiments being performed in CERN and in Fermilab where you might produce these scalar particles with strong magnetic fields. So you send light through a strong magnetic field, and you may find that my photons, they decay into these scalar fields. So these are axion-like particles, for instance. So, and maybe that one could be the dark energy candidate that I will be talking about here, or this gravitational. So, yeah, so the whole idea here is in fact to try to find where are these scalar fields, where can we see them, where can we detect them. So that's what's going to be my talk about, but I will focus only in cosmology. But if you want at coffee break or at lunchtime, I can tell you about laboratory experiments. So there are people doing laboratory experiments to also detect these particles, this particle scalar field, this extra scalar field. Okay, yeah. But just to put it in context, the models I'll be working here, they will have the standard model fields. Okay, so we'll have neutrinos, electrons, photons, the quarks, etc., everything, standard model fields, plus a spin-2 field, what we call usually the graviton, let's call it, okay, plus a dark matter candidate, cold dark matter. For me, it's going to be you can think of WIMP, okay, dark matter, weakly interacting massive particle, and my extra degree of freedom for gravity, so a scalar field. So these are all the fields, all the particles that I'll be considering in my lectures. Standard model fields, plus spin-2 field, the metric or the tensor, dark matter, and my scalar field, my modified gravity, and my scalar field hopefully will also drive the universe acceleration. So I'll be trying to focus on modified gravity theories which drive the universe acceleration. So like an alternative to a cosmological constant, let's say. And to be honest, it's not an alternative cosmological constant because I fine-tune all my model parameters to get basically the scalar field to behave as a cosmological constant, yeah? So there's a lot of work for you young people to do. The cosmological constant problem is not solved. I don't think it's going to be solved with my kind of thought. People in my generation, hopefully with yours, you will be able to do it. Okay? But just to put the scheme. Okay. I have until 10:45, yeah? Okay, so I was getting scared. Good. Okay, so there are then many ways to go beyond general relativity, basically violating one of these 4 conditions of the Lovelock theorem. So this is a plot from Tessa Baker. So one possibility is to go higher order gravity. So one of them that I will talk a lot in my talk is this F of R theories of gravity that I will tell you a little bit. So you will see that the equations of motion are not second order, but they do not have the Ostrodowski instabilities in there. You have also so-called F of G. So G is the Gauss-Bonnet term. So it's a curvature invariant, which in 4 dimensions goes away when you integrate and you apply the variation principle. But if you live in higher dimensions, it changes the equations of motion. Or if you have function of the Gauss-Bonnet term, then it survives and you survives the equation of motions and will have some effects and can be also a dark energy candidate. Then you have, for instance, higher dimensions. Then you can, for instance, you have heard about brain-world models like the DGP model, 5-dimensional model, random syndrome brain-world models. You have string theory inspired models. So these are all extra dimensions models. So usually you have in fact, so I should say that in these brain world models and even in these higher order gravity theories, they are equivalent to, many of them, not all of them, they're equivalent to include an extra degree of freedom to our gravity sector. So for instance, if you have an extra dimension, usually you have to compactify the extra dimensions. And one way to explain why we do not see these extra dimensions, and one way when you compactify these extra dimensions, usually you include a scalar field, which is basically becomes the radian or the radius of the extra dimension. So basically, the extra dimension is equivalent to the existence of a scalar field in my gravity interaction. So I will end up with a theory of modified gravity, which is a metric, or sorry, a spin-2 field plus a scalar field. So we have these extra dimensions. And then the one that I will basically focus a lot in my talk is basically to add a new field. And in particular, you can add scalar fields. And as you can see, there's a lot of different models in there. We have heard about the Ondesky theories here, and Galileans, for instance. I think maybe I've heard also about the Scalar-tensor theories and Brand-Sticky type of theories. So that's one way. But you, besides adding a scalar field, you can also include the vector fields. For instance, some very famous theories of gravity is the Einstein ether theory, which leads to Lorentz violations. And then you can also add extra spin-2 fields. So in biometric theories of gravity, for instance, where you have two spins, so you have bigravity, massive gravity, biometric mode. So for instance, this one is just an alternative. So they introduce another spin-2 field as an alternative to dark matter. So dark matter is not a WIMP, a weakly interacting massive particle. Basically, dark matter is a spin-2 field, for instance. So there are different ways. And of course, you have also the possibility of including a scalar field, a vector field, and a tensor field, the three of them together. So a very famous theory is the tensor vector scalar theory by Bekenstein, which is an alternative, for instance, to a dark matter particle. And of course, as I said, you have these four conditions for the Lovelock theorem, but you can just say, no, I don't believe in an action principle. And then you have other ways of approaching gravity, which I really don't know much about. Is like the emergent approaches, for instance, from Palmanaman, where gravity is just like a thermodynamical kind of phenomena. So it emerges from other fundamental, let's say, properties. So space-time is not a fundamental property. Maybe space-time is just a field which represents the time, and fields which represent space. And then gravity comes from an emergent property of those. I really don't know anything about that. But I think it's very interesting, and I think for me it's very nice that people do research in areas and go into directions which go against the mainstream in there. Okay, so I will not, of course, in my talk, I cannot cover all these theories of modified gravity. I will mainly focus on theories of modified gravity where I'm including a scalar degree of freedom. They are going to be somehow equivalent to these higher order gravities, in particular the F of R, which I will talk about, and also to some of these string models, especially dilaton type of couplings models. Okay, so let's now be a bit more specific of the models I will show you as an example. Again, remember, my idea is to give you a little bit of this theory, and then let's go for the observations, which will be maybe on the second or third lecture, in fact. Okay, so what I have is a theory of modified gravity where my gravity interaction has two carriers, let's put it like that. One is my tensor field, the G mu nu, the spin-2 field, and the other one is the scalar field. Okay, so an action is going to be a very typical action that you have seen. So we have the Einstein-Hilbert action, the R, the Ricci scalar, as you see. And then I'm introducing my scalar field. So my scalar field will have a kinetic term. In my model, it's going to be just a standard kinetic term. So it's going to be just like that. Okay? But in many, many other models, well, you saw the Galilean models, the kinetic term might be non-standard. So you might have a function here of the field as well, in front of the kinetic term. So, but the models I'll be working on, they're all standard kinetic terms. If I introduce a scalar field, usually I also have a self-interacting potential. Very often just a mass term. It's a half m square phi square term, because my scalar field, we look at it as a particle, although it's not quantized, so it has a mass. Yes? And then, since I'm doing modified gravity, it means that I have an interaction between my degrees of freedom, my gravitational interaction, with the standard model particles and the dark matter, just like electrons have an interaction with photons. Okay? So that means that my matter Lagrangian, and here includes baryons and dark matter, so these are going to be representing my dark matter fields and my baryons, okay? They will fill a geometry which is basically the G mu metric, that's that one, and some terms connected to my scalar field. Yeah? And that's going to be my coupling. And my coupling is going to be a conformal coupling, so it's only depending on the scalar field. In general, I could have my coupling depending on the scalar field and also derivatives of the scalar field. Again, as I said, I'm going to consider only conformal couplings. Okay? Now, when I introduce an extra degree of freedom on my gravity sector, it's like introducing an extra interaction. And at the Newtonian limit, what we will see is that my scalar field will introduce an extra force, which is going to be basically proportional to a coupling, to a strength. It's going to be basically the derivative with respect to phi of the log of this conformal factor here. That's basically the strength of my phi force. You will see how this comes, okay, a bit later. And, and also the gradient of my scalar field, the spatial gradient. Okay, remember that just in your Newtonian gravity, a particle acceleration was proportional to the gradient of the Newtonian potential. That's a force in classical physics. So if I have a new field or new particle, if it's easier for you to think about that, the force needs to be equivalent, proportional to the gradient of my scalar field. And this is going to be a very, very important point in my talks, as you'll see later. Okay? So my phi force is going to be proportional to the strength of the force, or the coupling between my scalar field and my matter fields, and proportional to the gradient as well. Okay, so the stronger is this coupling, the stronger the force is. Yeah. So usually, and that's a gradient, very good. So usually a phi force has two main properties. One is the coupling strength. Okay, there's going to be that part here, the coupling here to the standard model fields. So for instance, the strong interaction has a very strong coupling, the weak interaction is a bit weaker, electromagnetism even weaker. Yeah? And gravity really, really weak. Yeah? So the force, if this coupling term is very large, then this force is very strong. If it's very weak, the force is very weak. Okay, so it's the coupling strength. The other one is the range of the force. Forces, they have a range. Yes? Electromagnetism has an infinite range because the photon is massless. Well, in the standard model of particle physics, yeah? Maybe you guys will come up with a theory for electromagnetism, for QED, where the photon has a bit of a mass. Lots of constraints on that, so you can't be wild and crazy about that, but there's also massive QED. Also, in general relativity, the graviton is massless. Again, Antonio yesterday talked about a massive gravity, so maybe there's a mass for the graviton. And at the moment you introduce a mass, the range of the force of that carrier is not infinite anymore. It becomes, the larger the mass, the shorter is the range. Okay, so the range of the force is going to be something very important, because we're going to talk about tests in astrophysics. Yeah, so if the range is of a galaxy scale, that's very different if the range of the fifth force is just a few meters. Yes, so the effects of the force will depend on how long range or short range this force is, as you will see. Okay, so usually these are the two main properties of an extra force: coupling strength, range, and you will see in the theories of gravity I'm being considering here in this lecture, it's going to be important to when this force is active. In my theories of gravity, the force, you will see, it's not going to be always active. It will be a force that will be environmental dependent or time dependent. And you will see that. Okay? In there. Okay. So,
sorry, what if scalar field coupled with gravity non-minimally? We have again the extra force. I mean, in the first.
so if there is, you mean if there is no conformal coupling, then there's no force.
In the first bracket,
Yes.
I non-minimally coupled with the R.
Yes, I'm writing this, let's call it in the Einstein frame. Okay, so I just have the scalar field is minimally coupled to R, so it's not coupled to R. The coupling goes directly into the standard model fields and to the dark matter fields. That's a good question. So this is usually writing down the modified gravity in the Einstein frame. I can also remove, and I will show you how to do that in the next lecture, where I don't have any coupling here, and I put my coupling to R. And I coupled the scalar field directly to R. Yes, and these two approaches are more or less, well, equivalent, depending if the theory is conformal or not, or if you find that this formal relation between the two frames, yes, the Einstein frame and the Jordan frame.
So in that case also we have the extra force.
You do, yes, that's right. Even if you don't couple here and you couple to the R, very good question, yeah. So the effects are equivalent to an extra force, but maybe you don't think of it as an extra force. You just think as my geometry is different. So we can think, so one way of thinking is that, for instance, my geometry is just the, let's call it the Minkowski metric, where I have two particles which interact gravitationally, and there's a scalar fields which they interact the two particles as well. So it can be Minkowski metric where there's like an electromagnetic force. Okay, that's one way. Or the other way is to say, no, there is no electromagnetic force, so there's no scalar field force between the two particles, but the geometry is not Minkowski anymore. There's some curvature.
So in that case, why does it explain somehow is a dilaton field?
Yes, it's a dilaton type of field, yes. And yeah, I will show the equations, maybe it's going to be a bit more clear, yes. So I don't know if that was clear for the students, because I think it's an important issue. Is there a...
You want to use the...
Yeah, just to a quick... No, yeah, well, okay. Just a little bit. Or maybe it's too much work for... I'm going to use it for 1 second. Is there... Yeah, just... Yeah, thanks. It's just I think that's enough. Yeah. So I think the question is relevant to have you the physical intuition. Yes, that's what I want the students to have. So one thing is, you imagine you can have a flat metric, where I have two particles, and they interact via the metric. Let's say, okay, the G mu nu. And if there is a scalar field, an extra degree of freedom, they will have the scalar field there as well. Okay? So this is the way so that's the way I'm writing Lagrangian there. Okay, that's the way I'm writing that Lagrangian. So basically, so the metric of the spacetime is just R, G mu, and then I have an interaction between my standard model fields, which are these two particles here, my two electrons, let's say, with them. The other possibility, that's what Nasser mentioned, is that let's forget these scalar fields, so we don't have this extra interaction here explicitly between the standard model field, between the electrons, but then absorb this scalar field into the space-time metric. So now my flat won't be flat anymore, but there's going to be some kind of curvature in there. Okay? I'm not being completely honest with you because there's some issues here, but that's another way, it's another way of seeing this. So this is called maybe the Jordan frame way of seeing things, where all my extra interactions, they go into a coupling to the Ricci scalar. And the other one is the Einstein frame, where I keep my spin to the metric and I just add extra forces. Is that okay? So, for instance, if I have two particles on a flat space, like here on this room, I have two electrons here in this room. They feel gravity because we are in the room, so we are on Earth, so they have to feel gravity. But if there's a magnetic field in the room, they also feel this magnetic field, mu vector. Yeah? But I can say, so I will see my electrons moving in a strange way. Imagine that I didn't know there was a magnetic field, but I throw the electron in the room, I will see the electrons moving in a strange way because there's a magnetic field. But imagine I didn't know. So that way of seeing things is like, okay, I don't know there is a magnetic field. So if I see my electron bending, for instance, that means that maybe I would say, oh, maybe my gravitational field here in this room is strange. So I have some kind of geometry going on. So I have some kind of curvature that I'm not seeing. Okay, so that's the two pictures basically to see. And I'm not completely honest because it's not always equivalent, these two pictures, because you can have couplings. Some theories are very complicated. You have couplings to the Ricci scalar, and then you have extra couplings to the Mota field. So things get very, very complicated. As I say, theoreticians, we have a lot of imagination. Yeah. So theories of modified gravity, they can be extremely complicated. But in the simplest case, that's one way of seeing. Yes. And these are called the so-called two frames: the Jordan frame or the Einstein frame. So two ways of seeing these pictures. Okay, I think yeah, maybe I should pause now. I'm only halfway through my first lecture, but yeah, I think it's better to take our time and to understand things properly. Okay, so let's do a pause because it's 1 hour, yes? No. So let's have a coffee and then we'll be back. Okay, thank you guys.
So about 15-minute break. Okay. Thank you very much.
Yeah. So you have to remind me to use the pointer because, you know, lots of things in my hands. Okay, so we saw that when you introduce the scalar field, I told you here in this slide that the scalar field introduces a free force which is proportional to the coupling, which is this conformal factor here that's doing what we call, and the gradient of the scalar field. So if we want to do, for instance, to know how galaxies cluster in the universe, how dark matter particles come together to form the fluctuations that you see on the cosmic microwave background radiation, you know these dark matter particles, they will feel this free force. So how strongly do they cluster? So it means I need to calculate what is the spatial gradient of my scalar field. Okay? So this is what I'm going to show you now. So how do you calculate scalar gradients? Well, let's start from the one that you know, like in Newtonian physics. So as I said, there is this Poisson potential, and the Poisson potential is a potential that, you know, let's say if the universe is empty, that's not quite true, but okay, let's say if the universe is empty, there's no matter there, there's no energy, it's just a constant. So if you take the gradient, it's zero. So there's no force if you don't create a source from this Poisson potential. But if you have some distribution of matter, yes, in the region of space-time, for instance, a massive object with a mass m, then this mass m will source the Poisson potential, okay? And that's the equation of motion for the Poisson field is called the Poisson equation, yes? So the Poisson potential is basically sourced by the way matter is distributed in some region of space-time. So, as you know, when I have some massive object, it will create a force on a given test particle that's going to be here. So if I want to calculate what's that force, I need to calculate the gradient of my field. So usually what you do, you can assume spherical symmetry, makes our problem much easier to solve because I have to solve basically a differential equation. I have to solve this Poisson equation to know what's the value, that's the solution of my Poisson field given a given distribution of matter. Yes? So I'm assuming spherical symmetry. I'm assuming the so-called quasi-static limit, so I'm dropping time derivative, so I'm going to just assume that my field is static, so I'm just keeping the spatial derivatives. And the solution that you get, that you all know, is basically the 1 over R solution for the Poisson field. Yeah? That one, you did it maybe even in high school. Okay, so there's a gradient of 1 over R, so that means when I take the gradient of this, you'll get the Newtonian force. That's the one that you know.
Sorry, I have a question. Why Poisson equation is second derivative? Why it's not fourth derivative?
I didn't understand the fourth derivative.
Yeah, Poisson equation. It's second derivative.
Yes, it's second derivative. Yes, this one?
Yeah.
Yeah.
Because you know the weak field limit of higher curvature is not second derivative, it's fourth derivative. So my question is there any fundamental reason the Poisson equation is?
Well, there will be, again, you asked for the fundamental reason, which is very good. The answer?
Because, you know, we have an experiment. That's not satisfying.
No, yes, I don't know if there is a fundamental reason. I don't think we have. Here, I'm just assuming, because that's Newtonian physics, Newtonian gravity, that's what I'm assuming here in this slide, and I'm going to just that's assuming Newtonian gravity. And even when you use general relativity, when you linearly perturb the Einstein equations in GR, you get some equivalent to the Poisson equation as well. This is what I'm assuming here. Is this correct? Is there, I don't know if there is a reason, a fundamental reason for that. I don't think anyone knows. So it will be good to try to find out. But we can test, yes? We can test that. And that's what I'm going to try to also show you some tests.
Yes, yes. I'm asking because, for example, for quadratic gravity, pure quadratic gravity,
Yes.
if we take a weak field limit, we go back to the fourth derivative, and when we solve fourth derivative, beside this term, we have an extra linear term. And that exactly solves the dark matter.
Ah, okay. Yes, yeah. Yeah, but you start with already with the quadratic gravity, yes? So I guess your equations would be modified, yes. I will show you that these equations will be modified as well in modified gravity, but not, now I'm just assuming the usual, that's just Newtonian physics, simple, yeah.
Also, it has been shown by Steel, the mass theory.
Mm-hmm.
All quadratic gravity, the dimension of all quadratic gravity is 0, and therefore quantum part of the zero normalization.
That, I don't know that, yeah.
Okay.
But tell me at lunchtime, so, because I'd like to know about this paper. Yes, Dustin, I don't know, yeah. Okay. All right, so here is just simple Newtonian gravity, yeah? So you have seen this in your high school, yeah? You can get the 1 over R for your Newtonian potential. Now, the question that comes is that, okay, if I have now a test particle, what is the acceleration that this particle will feel in there, yeah? So this mass creates the Poisson potential, so created a gradient there, and then I put a test particle, and the question is, what is the acceleration of this test particle? Well, as I told you before, in Newtonian gravity, we have this kind of equivalence principle, so which says that the Newtonian potential, which basically will tell me what's the acceleration of the particle, it's going to be equal to the Poisson potential. Okay? So what it means is that if I solve the equation for the Poisson potential, it's going to be the G 1 over R. Yes, it's going to be 1 over R. Then I say that my Newtonian potential is just Poisson potential, so my acceleration is going to be basically the gradient of 1 over R. That's your Newtonian physics. That's what we did. Now I'm explicitly showing you the Poisson field, the Newtonian field, because it's going to be important in my theories, okay? Because they are going to be different. Okay, very good. So yeah, so what happens then when I solve my Poisson equation, assuming this kind of equivalence between the Poisson equation, the Poisson potential and Newtonian potential, then my acceleration is just the gradient of the Newtonian field by definition, and by equivalence is equal, the two potentials are the same, so then my acceleration is going to be 1 over r squared. And that's Newton's law for gravity. Yeah? The force, gravitational force, is just 1 over r squared. Okay, that's what you get. Okay, what happens now for my scalar-tensor theory of gravity? So a theory of gravity where I have an extra scalar field which is coupled to matter. Okay, because I told you that my scalar field will also have a force which comes from the gradient. So now I'm going to show you the same exercise that we did right now for Newtonian physics. That I hope you have seen that before. Yeah. Let's do the same exercise here. Okay, so I have my action for my field, my action. So I have the usual Ricci scalar. So that's the Einstein-Hilbert action. That's the normal one. And I have my scalar field with the standard kinetic term. I have a self-interacting potential. Some people call it as well the bare potential. And I have my matter Lagrangian, where I have my standard model fields and my dark matter fields. That's why there's I there. I can go for electrons, neutrinos, the wind, dark matter, quarks, whatever. And I have my coupling, my matter fields. They fill a geometry of space-time, which is given by this GI metric. And this GI metric is basically a relation, which is a conformal relation between the two metrics. Yes, the G mu one, that's the one where I build my Ricci scalar. And now I have a function, which here I'm explicitly showing you this function, so it's not just a general function, is a dilaton type of coupling. So because usually it's inspired from string theory when you compactify the extra dimensions, and you have these so-called dilaton models, which is the exponential of the scalar field. And you have these coupling constants here, beta I, which basically tells you how strong is my scalar field to my matter fields. So if beta is very large, then the coupling between the scalar field and my matter fields is very strong, so I have a very strong field force. If beta is very small, or 0, if beta is equal to 0, then GI is equal to G mu nu. Yes, so we recover general relativity if beta is equal to 0. Yes, so we just recover general relativity and with a scalar field in the universe. Okay, so that's the way. Good. So this is my Lagrangian, my action, and with this conformally coupled theory. Sorry about the jargon, conformally. I use it, but hopefully now you are okay with this jargon. Okay, so what do? Well, I apply the variational principle to calculate what's the equation of motion for my scalar field. Okay, so this is just the Klein-Gordon equation for a scalar field given this metric. If I vary with respect to the field, if I vary with respect to the metric, I get the Einstein equations for this theory as well. Okay, but since my aim, I want to calculate what's the gradient of my scalar field, because that's what's going to give me the fifth force. And I want to know the fifth force because I want to know how galaxies cluster in the universe. I'm a cosmologist. Okay, so this is what I want to know. Yeah, so I need to know this gradient. Okay, so I have my Klein-Gordon equation. The Klein-Gordon equation is the box phi, so this is basically time derivatives and spatial derivatives, as you know. Okay. You have the first derivative of my bare potential with respect to phi. This is just v prime. Okay, I think I've seen the Klein-Gordon equation before. And now I have this term, this extra term usually that comes from the interactions between my scalar field phi and the energy momentum tensor, T mu nu there. Okay, for the different fields. And here I'm assuming that beta is not a constant, but it's beta I, so it's a constant, but it can be different for different matter fields. Okay, because nobody told us that my scalar field should interact with the same way with all the particles in the universe. Maybe my scalar field interacts very strongly, I don't know, with the electrons, but very weakly with neutrinos, or very weakly with quarks, or very strongly with dark matter. I don't know. So, in general, I can write my scalar field and the interactions with the different parts as a beta I, where beta can be different from different particles. You know, neutrinos, they don't interact with all the particles in the Standard Model. Yes, photons, they don't interact with all the particles in the Standard Model. So, it's like that. Okay, so that's why I have a beta I. I will make my life easier because I will make this beta I just equal to beta, so the scalar field interacts with all fields in the same way. But that's just to make my life easier, okay? And it's much easier to solve the equations as well. So this is what I'm going to do in my talk, but in general, I can have my scalar field interacting with different particles in a different way. Okay, so I'm going to assume as well, very classical case, where my self-interacting potential or the bare potential is just a mass term. Okay, so my scalar field has a mass m, okay, and has some interactions like conformal kind of, we call this exponential type of interaction, or dilaton type, to my Standard Model fields. Very good, so I just need to put this in here, and I will try to solve the Klein-Gordon equations to know what's the gradient of my scalar field. So let me try first find the gradient of the scalar field, just like in the Newtonian case. So I'm going to assume first that I'm on a flat space, just like on my Newtonian case. It's going to be static, so I'm going to neglect time derivatives of the scalar field, so I'm just going to consider spatial derivatives. I'm going to assume an homogeneous body with a given mass, with a given density, and that density is constant. Okay, so really to make my life very easy, and spherical symmetry. I'm going to assume a spherical object, just like what I did for the Newtonian case, for the Poisson field, okay? I just want to know what's the profile of my scalar field in this case. So for the Newtonian case, I got 1 over r. You remember that was the solution for my Poisson equation. Now I want to know what's the solution for this equation. And this equation is going to be a bit different because the equation is a bit more complicated. Yeah? So if you write down its spherical coordinates, if you neglect all the time derivatives, you only have the spatial parts. And the right-hand side, that's the 1. So I only have like the derivative of my bare potential. It's just a mass term, the mass of the field. Beta now is a constant, just 1 to all the matter fields, okay? My rho is the function of r because I have a spherical object here, which has a given density, rho critical, has a given radius, and then in the outside, the density is going to be different. For instance, it's going to be the vacuum, or the critical density of the universe, okay? For instance. So, and I have my coupling, which is this exponential of the field. M Planck, okay, I didn't tell you, this is just to make my equation dimensionless in terms of the field. Okay? That's M Planck, it's just a constant, so my field I can put it in units of Planck units because it's easier to think about that, for some people at least. Also, to give you an example, when beta is equal to 1, in Planck units, it means my scalar field, this fifth force, has the same strength as gravity. So it's very weak, but it's the same strength as gravity. Yes? So if I want my scalar field force to be with the same strength as the electromagnetism, I need to, beta needs to be 10 to the 30. I can't remember, or more. Yes? Electromagnetism is much, much stronger than gravity. So beta needs to be values of 10 to the 30. But I'm doing modified theories of gravity, so I want my coupling constants to be more or less at the same range of values as the graviton. Otherwise, people might ask me, well, why does the graviton interact with order m Planck, and my scalar field, which is a gravitational field as well, interacts 30 orders of magnitude higher? That would be a very unnatural way. And there's problems maybe for you who did quantum field theory called the hierarchy problem of the interactions of nature. That's one of the problems, why you have the strong interaction so much stronger than the gravity, or even the weak interaction and the electromagnetic interaction, much stronger than the gravity. Okay? So in order to not make this problem even worse, beta is going to be always around 1 in this talk. So my scalar field is a gravitational field, really. Good. Okay, so let's solve this equation. And one of the exercises for your tutorials, if you want to do it, is you try to find the solution that I'm going to show you here. So the solution is, I'm not going to show you for sure, I'm not going to do it here. The solution will come by assuming some conditions. So the conditions that my scalar field will reach a constant value at the infinity, very far away from the body, phi infinity. Okay, and in the center of the body, the gradient of the field will go to 0. So I will get stable, like the field will reach to its minima there in the center of the body. Okay, so when I solve the equation with these boundary conditions, what I get is a solution more or less like that. So the spatial, that's your tutorial for tonight. So the solution for your scalar field is going to be a constant. That's the value at infinity when r goes to infinity, so outside the massive object. So when r goes to infinity, all this term goes to 0. So my scalar field will reach a constant, okay, outside the body. And inside the body, as we come close to 0, you will see this kind of exponential term here getting there, with 1 over r there as well. Okay, so the profile of the field is a 1 over r times this exponential term, where m is basically the mass of your field. Remember, the self-interacting potential is just 1/2 m squared phi squared. So that's the mass of the field. Very good. So now that I have the profile of the field for a massive object, just like I calculated the same for the Poisson potential, then if I have 2 particles, I can calculate the force between 2 particles. Yeah, so let's imagine that I have 2 particles here. I'm doing cosmology and classical physics, so I'm saying here this can be protons and electrons or neutrons or neutrinos, but in reality, these are going to be massive objects, like in cosmology, each particle is like a galaxy or something like that. Okay, so very big. So, but this is just to give an example that I have 2 particles, so they will interact gravitationally and also via this scalar field, which has a mass m. Okay? So you can calculate the force from this scalar field using quantum field theory. So like assuming a Feynman diagram, you can calculate the propagator of the force. Okay? But from classical physics, it's quite equivalent. You just assume that you have a scalar field from one of the particles with a given mass, a given radius, and another one classically. And so the force between 2 particles is basically given by that. Okay, so it's a force for the scalar field, is just the gradient of the potential of the field. Okay, where I'm assuming that each of these particles, they might couple to the scalar field with a different strength, if the 2 particles are different, for instance. As I said, in the rest of my talk, beta 1 and beta 2 are going to be the same. Just now, I want to explicitly tell you that the most general case is that this scalar field couples with different strengths to different particles. Okay? Very good. So I know the profile, so the force comes from there. And basically, it means that 2 particles in my universe, they will feel a total potential, which is basically equal to the Newtonian potential. Sorry. That's the Newtonian potential. Yes, it's just 1 over r term, plus the scalar field potential, which is called as well the Yukawa potential, or Yukawa correction, if you heard about it. Yes? So Yukawa did that in quantum field theory because you can get the same equations, but also in classical field theory, you have this Yukawa correction to your Newtonian potential. And as you can see, you call a correction. The Newtonian potential is proportional to the coupling strength, the beta. Yes, so if beta is very large, it means I will change a lot my Newtonian potential. And is inversely proportional to the range of the force. Lambda is going to be the range of the force, which is just 1 over m. So the larger the mass of the field, so let's look in here. So there's a m is the mass of the field, yes? So if the mass is very large, it means this exponential goes to 0. Yes, so the field becomes very massive, so it means the range of the force becomes very short range. Yeah? And that means the force is a very small effect. You can imagine my arm is my range, so if I have a very long arm, I can get the people from the back and pull them towards me. I have a very long range force, so I affect a lot the universe around me. So you can imagine you guys are galaxies. If there is a force in the universe, a scalar field with a very long range, it means galaxies which are really far away, they will feel this field force and they will cluster a lot. If the range is very short, it means if the mass of the field is very large, then the range becomes very short. And so my effects, because of this force, are going to be more local effects. So large-scale structures of the universe will not be affected so much. I will go back to that, but just to give you, pointing out the importance of the mass. Okay? So there's something very important here, is that as you can see, the force does not go as 1 over r squared, which is the Newtonian limit. Moreover, the force, if I have this scalar field which has different couplings for different particles, so let's say B1 is the coupling to a dark matter particle and B2 is the coupling to a fermion, to an electron, then it means the force depends on the constituents. So you have equivalence principle violations in there. Okay, so that must be, I hope you are now thinking in your head, okay, this guy is a bit crazy. He's proposing me a theory of gravity which does not go as 1 over r squared and leads to equivalence principle violation. So the force depends on what I'm interacting with. Okay? This should put the red alert in your heads. Okay? So remember, in Newtonian gravity, what we have is 1 over r for the Newtonian potential. The force is just given by 1 over r squared. Since we are in gravity, this is just equal to m to the acceleration, yes? So the acceleration of a test particle basically is independent of the mass of that test particle. That's the equivalence principle, yeah? Okay? So we have independence of the mass, and we have the 1 over r squared force. That's Newtonian gravity. If I have scalar-tensor theories, that's very, very different. So my potential does not go as 1 over r, it goes as 1 over r, and then there's this exponential term here, where alpha is basically the coupling between the two particles. Lambda is the range of the force, as I told you, yes? My force then is going to be, you can be as 1 over r squared, but then my effective g, my gravitational constant is not a constant anymore. You can also look at this picture, but depends on where you are, depends on the position. Yes, my effective g, you can write it as a constant, the Newtonian one, plus a term like that. So exponential of minus r over lambda and that one. You don't need to memorize this. What I want to point it out is that now I have a force in nature on the gravity sector. So my gravity now is not independent of the masses. It's not independent of m1 or m2. Will become dependent and does not vary as 1 over r squared. Okay? So if I do an experiment where I can detect that, that means that Newtonian gravity and even general relativity is not the right way of describing the universe. Yes? So people have been doing lots of experiments to try to detect these kind of effects. So deviations from the 1 over r square and composition dependent forces. And these kind of experiments have been very old, like from Galileo with the Pisa Tower, you know, dropping objects on a gravitational field and see if the rate, the acceleration of these objects is the same independent of the mass. Yeah? So that's one of the tests of the equivalence principle. And much better than Galileo, even recently, people have been doing a lot of experiments with different kind of apparatus to calculate whether the equivalence principle holds or not. For instance, that gravity, it does not matter whether one object is much heavier than the other one, it should drop at the same rate. The acceleration should be independent of the mass. People are quite smart nowadays. They have been even doing experiments, which I really admire these people, with neutrons. So they produce neutrons, and that's in CERN. They produce neutrons. They cool down the neutrons and put them on a box. Yeah, neutrons are really tiny particles, if you know, and neutrons pass everywhere. Yes, so they cool down the neutrons so that the wavelength, they create like a kind of a condensate, the wavelength of the neutrons become very long, and if it becomes very long, basically they can be trapped in some boxes. Yeah, so they cool down these neutrons, and then they make these neutrons, which are they are kind of a condensate, so they have very long wavelengths, to bounce these neutrons in mirrors, and then can track the trajectory of these neutrons throughout the experiment, and they know what they should expect for the usual Newtonian gravity, so they measure if neutrons in a gravitational field, they follow a different path, to try to detect, for instance, if neutrons feel gravity in the same way as other objects, for instance. Yeah, it's quite impressive. You know, cool down neutrons up to the point you can bounce neutrons. Because if I drop a neutron here, just will go through the table. Yes, you know that. You can drop a neutron, which just go through the Earth. Say they cool down so the neutron bounces on a mirror. It's unbelievable. I don't know how they do that. Yeah. And another experiment they do is with atoms. This is called atom interferometry. So they have these vacuum chambers, which they have some massive object here, and they throw atoms into the vacuum chamber, and they split the beam of atoms in two different trajectories. One goes up and one goes down, and the atom's trajectory which goes down will feel this massive object, so will feel a stronger gravity pull than the atoms that go on the upper trajectory. Okay, so the trajectory, these atoms will be a bit slower down because they will have a longer path. They will have a longer path because they will feel the gravity more than the other ones. So they will fly in a longer path. And then they make these two beams of atoms, they split here with the mirror, they make them interfere here in the interferometer and see whether they are still in phase or out of phase. And they should be out of phase because this beam of atoms, they go closer to this massive object. So they have a longer flying time. So they know accurately what should be Newtonian gravity should do to the path, to the trajectory of these atoms. So they know what should be the phase of the atoms when they meet. Okay? So they do these kinds of experiments to try to detect gravity, whether does gravity change if you are using atoms or neutrons of massive objects or not. Okay? And up to now, nobody has found any deviations from the 1 over r squared law, nor a composition-dependent gravity. So everything confirms Newtonian physics at these laboratories of general relativity. We did even better. We went outside the laboratories to do experiments of equivalence principle in the solar system. So the funny one was when they got to the moon, they dropped the feather and the hammer, you know, just for fun, of course, not an scientific experiment, to see that both of them fall into the gravitational field independent of their mass. But there's two extreme experiments, really important. One is the microscope satellite experiment, where they have a torsion balance that is an extremely accurate test of the equivalence principle as well. I will not go into details here. And there's also the Cassini probe, which is a probe that went out in the solar system to do some experiments, some measurements of some planets. I don't know, maybe someone knows. But people who work on gravity told them maybe we can use the Cassini probe because it will send signals to Earth, and we want to know, we know it's going to go through the geometry caused by the sun. So the light signal, we know the trajectory very well, the light bending. So we will know how this signal should bend around the sun, and that's a test as well for general relativity and the equivalence principle, and the so-called PPN parameter, which I will give you the details later. So I'm not going to go into details now, but just to tell you that even in the solar system, general relativity is a fantastic theory of gravity. So if you modify gravity, if you go beyond general relativity, including scalar fields or extra dimensions or whatever, in the solar system, on laboratories on Earth, you need to recover general relativity. Okay? So I'm now stuck in a problem because I'm spending 5 hours of our lives talking about theories of gravity which go beyond general relativity. We have this scalar field which does not go as 1 over r, as this exponential, this Yukawa correction there, and it's composition dependent. And all these experiments, what they tell you is that if you really want to work on this theory of gravity, what the bounds tells you is like, so the y-axis, that's the strength of the coupling, alpha, so it's my beta, sorry, now here is alpha, and here is the range of the force, so the Compton wavelength of my scalar field, which is the range of the force. And what these experiments tell us is that if my alpha is of order 1, so if my scalar field couples to my standard model field, so dark matter, with the same strength as gravity, then that means that my Compton wave range needs to be very, very small, 10 to the minus 4 meters. That's basically what it tells you. If my coupling is larger, then my Compton wavelength needs to be much, much smaller. This is what these experiments all tell you. So I can have a scalar field in my theory of gravity, but then this alpha needs to be either very close to 0, yeah, because so we don't have this correction, this Yukawa correction, or the range of the force needs to be really, really small. So this exponential basically is 0 as well. Okay? So if you do modify gravity, you either have a strong coupling, so of order 1, but then the range needs to be very short, or you have a very weak coupling, and then you can have a very long range. But you cannot have a strong coupling and a very long range, because otherwise you would have seen it with your neutrons bouncing on a mirror, for instance. So I didn't tell you that because I think it was told by Antonio, maybe some other lectures. We are doing modified gravity, well, for the fun of it, okay? We like to do mathematics and look for fundamental reasons why things happen. But one of the biggest motivation of modified gravity is to explain what is dark energy, yes? Or to explain what is dark matter. So we want a modified gravity where the effects are not at scales of a millimeter. I do not want to change GR at a millimeter scale, because that does not affect my universe at very, very large scales. If I want dark energy, I want a modified gravity which will affect the universe at very large scales. If I want a dark matter candidate, I want a modified gravity that will expect at galaxy scales at least. Even the CMB, the cosmic microwave background radiation, I need the dark matter there, so I need to explain those kind of effects. Yeah, so I want a long range force. I want a force which is several megaparsec or even gigaparsec range. So I want lambda to be very, very big, huge, huge. But that's basically, if I have a very long lambda, these experiments tell me, well, then the coupling basically 0. But I want a coupling because I want, to explain dark matter, I want stars to move fast in my galaxy. Yes, so either I put dark matter or I change gravity, and having gravity there, it means I want my galaxies to move faster. So I want a strong fifth force at my galaxy level. But they are telling me, no, that's not possible. Okay, so how do we do that? I'm a bit lost. Okay, so how do we do that? I need to change my theory in order to incorporate something in it where evades my laboratory and solar system constraints. And what I need to do, I need to change the range of my fifth force and the mass or the strength of my fifth force. And this is what I have to tell you. So I will have to do something to this Lagrangian where I need to play with the strength here in general. I need to do something to it because my strength needs to be almost zero on Earth in the solar system, but needs to be strong at cosmological scales. And because that my strength, that's what's going to come here in my Yukawa correction there. Yes, I need to make it something there. And I need to play with my range in there. I need to do something to this theory. And the range comes, I should tell you, is just the Compton wavelength of my field is just 1 over m. Okay, where m is the mass of the field. Very massive fields, lambda is very small. Yeah, that's what I told you. Yeah, and the mass comes basically from the second derivative of the potential. If my v is just 1/2 m squared phi square, you know, m squared phi square, if I derive twice, I get m. So that's the mass of my field. But my scalar field, the equation of motion for my scalar field, the Klein-Gordon equation, as you saw it before, and that can be an exercise for you as well to do tutorials, it's box phi, and then we have the derivative of sum of effective potential, not just the bare potential, it's the effective one, which I show you to be the bare potential plus these interactions. If you remember my slide, yeah, let me show you. Yeah, so it's the box, and this is basically some kind of effective potential here by bare potential plus the interactions. Yeah, so it means that my mass is basically the second derivative and the square root of my effective potential. So the mass of my field is just not the constant, but it's something that will going to be related with interactions, my effective mass of the field. And this is going to be a key property from what I'm going to tell you next. Okay, so remember, fifth force, two quantities, the strength and the range, and I need to do something with them, otherwise these theories are completely ruled out by experiments. So this is now my second lecture. I need to to find the slides again, sorry. Yeah. Okay. My second lecture is about so-called screening mechanisms. So I told you, so I don't need to revise this too much. But I told you that if I have a scalar tensor theory of gravity, so besides the metric, I have a scalar field, and my scalar field will introduce a fifth force there. So the total force felt by particles is Fg plus F And we calculated that if I have my scalar field as a mass m, the total potential, and from that the total force that two particles will feel in my universe is just the Newtonian one, which is 1 over r, and the field, phi of r, which is going to be the Yukawa expression. Okay, that's what we did in lecture 1. And I finished the lecture saying we do extremely precise experiments in laboratories and the solar system, and we don't see these corrections. Okay? So how we get along with this series if we still believe in this series of gravity? we can do that. These theories are viable if they have incorporated in that something called a screening mechanism. Screening just means hiding. It's another word, let's say, for hiding. So I can screen myself away if I'm hiding from you behind the board. I'm screening away. Now you can't see me, yeah? So that's what I have to do with these forces. If there is a scalar field, creates a force, if I do an experiment in my laboratory on a solar system, I have to hide this scalar field from my experiment. Otherwise, I would see it and detect it. So I have to screen it away. And that's where the word screening comes from. So I need to change my Lagrangian for my scalar field in such a way that I have a screening mechanism in it. All right, so let's look at it. So I showed that the total potential that two particles would feel is the Newtonian 1 plus the Yukawa. Okay? This expression is only true for that very simple theory that I showed you. A standard kinetic term, a mass term potential, and a very simple interaction. If I have a general, well, not completely general, the generals are the Orndesky theories, but if I have a theory which have a non-standard kinetic term, so this is the standard part, if I have a non-standard kinetic term, so I have phi's and derivatives of phi there, I have a general self-interacting potential, so now it's not just 1 over m squared phi squared, you can have some interactions. And I have a general coupling to the matter field. So here I'm coupling to the trace energy, to the trace of the energy momentum tensor. Okay, so if I have this general coupling, the solution for this Yukawa correction is a bit more general and looks like this one. So the solution for the Yukawa correction is not just a coupling constant mr, it's going to be this general function here. Yeah, you can do that on the tutorials if you want as well. This one I think is a bit more complicated. So I don't advise you because it will take you several days to do it, but you can try. So what does the solution says? It looks like the Yukawa correction that we saw before. So there's an exponential with a mass term and a distance. There's the coupling to matter, the energy density. There's some couplings to the T mu nu, to the matter fields, and then there's the speed of sound. Okay, there's some other things in there. Okay? So what we want is that when you perform an experiment with neutrons, for instance, or atoms in my laboratory, I don't see this V force. So I don't see that. I don't see the Yukawa correction. That's what we want. So we want to make this field to go to 0 in my laboratory or in my solar system. Okay, so what can I do? There are 3 main things that I can do here. And one of them is just to make this coupling G to the matter fields, this is just the energy momentum tensor of matter, to be very small. I can make G go to 0, for instance, and if G is 0, my coupling to matter fields disappears, and the whole potential in gradient for the scalar field disappears. So that's one option, very weak coupling. The other one is to have a mass of my field to be very, very large. If the mass of my field is very large, then this exponential goes to 0 very quickly, and the whole gradient of my scalar field goes to 0 as well. Yes, to make the mass very large. That's the second option. And the third option is to have what is called a very large inertia. So my non-standard kinetic term here comes as 1 over these terms. So if the inertia is very, very large, then I also make my scalar field to go to 0. Yeah? You see these 3 ways of screening my Yukawa correction, hiding my scalar degree of freedom in there. Good? So, depending on the way I screen my theory of gravity, my scalar field, I can classify my screening mechanisms in fact, 4 categories. Okay? So these are in general based on the field value or the kinetic term. So let me show you. So in so-called chameleon type of screening, which is applicable, as we'll see, to f of r theories of gravity, what I will play is with the mass of the scalar field. So every time my field is above a given constant, a given threshold, let's call it lambda, it's not the cosmological constant, just a given threshold. Yes, every time my field is above that threshold, the mass will become very large, and this Yukawa correction, or generalized Yukawa correction, will go to 0, because the mass is very large, so the exponential goes to 0. And that you will see is called the chameleon screening mechanism. And is applicable, for instance, to f of r theories of gravity. The other possibility is when the field is larger than, again, a given threshold that we will see. Well, the threshold is like the solar system of the Earth, basically, as you will see. Then the coupling goes to 0. So the mass can be still very large or very small, it doesn't matter, but the coupling will go to 0. And these kind of screening mechanisms, they include the so-called symmetron and the dilaton. Okay, as examples. The other possibility is not to think about the value of the field itself, but to think about the gradient of the field, the kinetic term. So when the gradient is larger than a given constant, so this first gradient of the field, then my inertia becomes huge, and this term also goes to 0, will vanish. And these are theories of screening, so-called, for instance, the camouflage, which was, I think, was proposed by Eugene Babitchev. I don't know if he told you about this camouflage. He's the one who proposed it first. And other like debionic, and these usually is applied to Mond type of theories, which are alternatives to dark matter, but also to dark energy. And the other possibility, and that's probably the most famous screening mechanism, was the first one, is the so-called Weinstein screening mechanism. And the Weinstein screening mechanism is a mechanism that the kinetic term becomes very large when the curvature is very high. So given above a given threshold of curvature, the Weinstein screening mechanism kicks in, and you kill the Yukawa correction. And the Weinstein screening mechanism is applicable to the Galileans that Antonio De Felici told you yesterday. They are viable because of the Weinstein mechanism, massive gravity, the DGP model, the brain world model. Okay, so that's the Weinstein screening mechanism. So these are different ways of screening to hide the field force when we perform experiments on Earth. Okay, so I'm going to focus only on this side of the classes of screening mechanisms. So I'm going to focus my lectures only on screening mechanisms which use the field value. And I'm going to use 2 examples, one the chameleon f of r gravity, and the other one is the symmetron screening mechanism. Those are the 2 examples that I'm going to give you, and all my tests of gravity are going to be based on these theories. Okay? Because I need to focus, yeah? 5 hours is not enough to go through the whole thing. Very good. So the first question that we need to know, I'm a bit lost in terms of time.
I think a little bit late, 5 or 10 minutes.
Yeah. Okay, because, but at what time are we supposed to finish?
12.
At 12. Oh, okay. 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 It's all right. Okay, so first, why and where do we need screening mechanisms? Well, we need screening mechanisms because we do all these tests and we don't see the field force. We don't see the scalar field. Okay? That's why we need. So we need really to hide the scalar field from here. And it's impressive because it's not only those tests that we need to hide the scalar field. Even at astrophysical scales, we have some experiments, like we have observations. These are not experiments anymore. These are observations. For instance, we have pulsars rotating around each other. So basically, pulsars are basically neutron stars which emit electromagnetic light. So they pulse. And it's such a precise observation that we can basically track the orbit of these pulsars very accurately. So these are two pulsars, which they have a mass of about 1.4 solar masses, and the other one is about 1.3. They have periods of 8 hours. Okay, so they move around in 8 hours. They do the full cycle. And since they move around each other, they create a quadrupole, so they produce gravitational waves. I don't know how's your general relativity. So they produce the gravitational waves, so they lose energy because they lose gravitational waves. And that means they get closer and closer together as time goes by. And the orbit decays about 75 microseconds per orbit. Okay, so it's a really tiny decay, but since it's only 8 hours, people have been tracking these pulsars, and that's the dotted line. So that's basically the shift of their orbit over time. So they've been tracking them since the 70s. So the dots are the experiments, and the error bars are inside those dots. So the error bars are really, really tiny, as you can see. It's an extremely well-constrained orbit. So they've been seeing these orbits for decades now. And the solid line, that's the general relativity prediction when you have two pulsars rotating and losing energy through the gravitational waves. So general relativity fits extremely well this observation as well. So again, I hope I'm not wasting your time talking about modified gravity. Okay? So if we really want to do modified gravity, we need to screen away modifications of gravity in these pulsar systems as well. Okay, this is another place. So it's not just only on Earth, on the solar system. Even at those astrophysical scales, we cannot see, there shouldn't be deviations from general relativity. So if you have a scalar field, you need to hide it somehow. But there's more. You know, we have now detected gravitational waves, yeah, since 2015. And the waveform of these gravitational waves just matches general relativity beautifully. Even the speed of the gravitational waves now, we can measure, is pretty much the speed of light. So again, the propagator of these gravitational waves propagated at the speed of light, so they are massless. So again, it's another confirmation of general relativity, even at astrophysical scales. So if you want to do modified theory of gravity, we need to have a screening mechanism which will hide the scalar field in these experiments as well. So this is where we need. Okay? So basically, we need to have modified gravity. It should recover general relativity in high curvature regimes, basically. Black holes, high curvature regimes. Pulsars, high curvature regimes. Solar system is still a high curvature regime with respect to the background universe. The Earth is also a high curvature regime with respect to the background universe. Yes, the energy density of the universe is very low. So the Earth is several orders of magnitude larger. The solar system as well, even a galaxy it is. Okay? So we can do modified gravity to affect the universe as a whole. That's fine. But every time we come to high curvature regimes, high density objects, we need a screening mechanism. We need to kill that Yukawa correction there. And visually, this is the best way for you to see as a student. Okay? So this is the job of screening mechanisms. It is in the general large-scale universe, where the density is about the critical density of the universe, like 1 proton per cubic meter or something like that. We have the gravitational force, and we have a very strong field force. The scalar field is active, is affecting structure formation, and is driving the universe acceleration. As we go to higher and higher densities, the fifth force, for instance, can become very, very short range, or the coupling can go to zero. And with that, I'm hiding the fifth force in there. Okay? So how do we do this in practice? We are theoretical physicists in general, I think most of us. So we want to have that kind of thing on a Lagrangian, yes? We do not want to change by hand the fifth force here and there. We want to have a dynamical way of hiding this extra degree of freedom. Okay? So this is what I'm going to do. So we have to play with the range and the strength of the fifth force. Okay. And okay, maybe I'll stop here. Is 1 hour? Yes?
Yeah, it's okay.
It is. And when we come back, I'll show you proper equations to how to do the screening mechanism for this series. Okay?
Okay, thank you very much for really nice talks. And I think we have lunch out there, and we come back at 1 p.m. exactly. Okay, and then if you have some question, you can ask in the what do you call cafeteria? Yeah. Okay, let's go.
Can I leave my laptop here?